All right, so I wanted to talk a little bit about the Tuesday plan and also some strategies here going forward for electron configurations. Did also want to mention that I've changed up the last bullet here. We were going to do, I was going to do a group activity with whiteboards using this handout, which you will get when you're in class. We've done this before with concept check, where you kind of consider the terms before you start studying them, and then you consider the terms after you've studied them. And we're trying to move towards plus, meaning you feel like you're an expert, or at least a check. That means you've heard of it, you know something about it. So most of these terms I think you've come across at this point. They came up in the reading that was assigned yesterday. So my plan was to have you kind of group up and either do a concept map with these terms or a 30-word gist summary. But I'm going to try to just scratch that for now. I really, since we've had some cases here at the high school, and I don't want anyone to get quarantined over this activity, this is going to be optional. You can do it individually, and you would just need to, again, write up either a concept map using these terms or a 30-word gist summary. And I changed the assignment on Schoology so that you can submit it online. Okay. So that these are terms you need to know, and if you do that activity, I think it'll help you prepare, but I'm going to call that optional at this point. Okay, so let's talk about some strategies with electron configurations. So what I have here are some different ways we have figured out where to put electrons in atoms. We looked at really the Atoms game, the Playmada game first, and you didn't really know it at that point, but it kind of forced you into some rules that we could make note of. If you go back to that activity, you had to put your first two electrons in this circle, and that is the 1s orbital. Your next two electrons had to go here, which is the 2s orbital, and then you could put 6 more electrons in the 2p orbital, and then we went down to 3s and 3p, and then this orbital is blocked until you put 2 electrons in 4s. And then this one opens up, it's the 3d orbitals. And then the next place we need to go for following the rules is 4p. And then again, this one is blocked until you put electrons here, which is 5s. That unlocks the 4d orbitals. And I don't think any of the examples that you did so far went that far, meaning needing to place that many electrons. But if you continued, you would be able to open up or put electrons in 5p, or S44p, and then again you encounter a locked set of orbitals, and you have to go then to 6s next. And then that would unlock, let me make sure I get it right, that would actually unlock these orbitals here, which are f orbitals. We haven't really talked about f orbitals much, and really, to be honest, in an introductory chemistry class, those elements are so uncommon, you really don't come across them too frequently. But once you place electrons in the 4f orbital, it unlocks the 5d orbital. Once you place them in the 5d orbital, the next place they would need to go is the 6p. And then it's not shown here, but there's actually a 7s orbital after that. I'm going to go ahead and stop because that gets you through the majority of the periodic table. But that was kind of a rules-based, game-based way of figuring this out. And then we kind of went to this Aufbau diagram where we filled in the electrons from top to bottom by increasing energy. And notice this one actually stops at 6s. So the game actually shows you a few additional orbitals beyond that. We also took that diagram and kind of turned it on its side for kind of a horizontal Aufbau diagram. And again, if you have these diagrams in front of you, you just work from lowest energy to highest energy. I wanted to share a way, however, kind of a trick that you can use to figure this out if you didn't have one of these diagrams in front of you. And what you do is you start writing out the orbitals that are possible at each principal energy level. So the first principal energy level only has 1s orbitals. The second principal energy level has 2s and 2p. The third principal energy level has 3s, 3p, and 3d. The fourth principal energy level has s, p, d, and f orbitals. Same for the fifth principal energy level. Sixth principal energy level. In the ground state, there is no F sublevel in the sixth principal energy level. And then in the seventh principal energy level, there are S and P orbitals. And there is possible to have 7D and 7F, but that would only occur in excited states, not the ground state for electrons. So once you list this, to get the order of orbital filling, you actually start kind of in the upper right and you draw arrows. So this will look kind of confusing at first, but what this shows is that the 1s orbital fills first, and then the 2s orbital fills next, then 2p fills, and then 3s fills, 3p fills, and then 4s. So that's kind of, again, that out of order where you had to unlock the d orbital by filling in the fourth 4s orbital. And then you get 3d, 4p, and 5s filling in that order. And then 4d, 5p, and 6s fill next. And then 4f, 5d, 6p, and 7s. And then finally 5f fills, 6d fills, and then 7p fills. So that is a way that if you can draw this diagram, you can also get the order of orbital filling that is reflected in, say, this diagram, or this diagram, or even in the Atoms game, the Playmada game. Doing those arrows, you can see the order that you had to fill them in the game. Again, you had to fill in that 4s orbital before the 3ds would open up. Likewise, you need to fill in 5s before 4d opens up. And so you would kind of continue on in that order. So I don't necessarily expect you to memorize the rules, but this is a way to kind of, if you had to work out the order and you didn't have a diagram in front of you, you could use one of those methods. There's an even easier method, though, if you just use the periodic table. Okay, so if you have your periodic table and you just follow by atomic number, you would start at hydrogen, then you would get to helium. And then if you look at your big periodic table, if you look at any of these elements, we said all of these end in S1, all of these elements end in S2. So sometimes this is called the S block, because all of these elements, their last electron is in an S sublevel. Okay. We noticed here too that the last electron went in the p orbital for these groups. So these are called the p block. And then the elements, the transition elements, the last electron went in a d orbital. So this is called the d block. And again, we're not too concerned about the F block, but it ends up filling, if you look at a periodic table, it depends how it shows it, but this one particular one has kind of a star here. After you get to barium, you actually end up going and filling up F orbitals. After radium, you end up filling f orbitals. So you can actually just look at the position on the periodic table to figure out the electron configuration. This whole column is going to end in S1. This whole column is going to end in S2. Helium is your exception. It ends in S2. This whole group would end in P1, P2, P3, P4, P5, and P6. And then again, I'm not so concerned, but if you're in this part of the periodic table, you're finishing up your electrons in an f orbital. So even though I'm not so concerned about it in terms of an introductory chemistry class, what fills after 6s is actually the 4f orbital. And periodic tables are almost always shown like this with the f block below. But the way it actually should be shown is something like this. See if I can squeeze it in here. So the periodic table actually, in reality, should be presented like this. And when you see it like that, you can see that you would fill the 1s orbital first, then you fill the 2s orbital, 2p is next, then you fill in the 3s in the 3p, 4s is followed by 3d. Again, that's that kind of quirk where you have to fill in the 4s orbital before you can unlock the 3d orbital. And then 4p fills next, 5s is after that, then 4d, then 5p, and then 6s fills, and that is actually followed by the 14 4f orbitals next. And then you fill 5d and 6p. 7s is followed by the 5f orbitals. Then you fill in the 6d orbitals, and then you finish up in 7p. So you might ask, well, why don't they show the periodic table like this? The real reason they don't show it like that is it's hard to put it on a poster or a sheet of paper because it's so long from left to right. So almost always you see it how we're used to seeing it. But in all reality, the f orbitals should actually be squeezed in there right in here. So these diagrams are helpful, but you don't really need them if you can read the periodic table in the way that you're supposed to. You just follow it through the S block to the P block through the D block, and you can figure out an element's electron configuration just based on its position on the periodic table. Okay, so if I were to just pick an element kind of at random, let's say germanium here, I already know that its electron configuration should end in 1, 2, 3, 4p2, because it's 2 blocks over in the p block, it's in the 4th row. All right, and then of course the rest of the diagram before that you can figure out as well. We talked about noble gas core configurations. If I were going to do germanium's electron configuration, the noble gas core approach says I'm going to take the previous noble gas, which is argon. So that's going to be the core of germanium's configuration. And then the next 2 electrons are in the s block, this part of the s block. So it's going to be 4s2. And then I hit the D block. Remember, the D block starts with the 3rd principal energy level. So 3d10 would be next. And then I'm going to end with 4p2. Again, the way I would finalize that is I would tuck the D orbital over to the left because it is interior. Those would be considered core electrons. So the configuration is going to be argon's configuration plus 3d10, 4s2, 4p2. And those are my valence electrons here. So those, again, are going to be your most important electrons for bonding. Okay, so The diagrams are great if you have them, but if you can read the periodic table properly, you can come up with a configuration like this just by really looking at position on the periodic table. Questions on that? Okay, let me go ahead and stop the recording.